we started this lesson by looking at a line that doesn't exist. We have these 3 data points, and we wanted to fit these 3 data points to a line. And what we found during that process is that, well, if the line passed through these 3 data points, we would be able to set up a system, but that system can't be solved. But what we have now is the theory of least squares. The theory of least squares says if you can't solve your system, look at the associated least squares problem. Instead of ax equals b, look at gramian of a times x hat equals a transpose times b. So let's recall that what our situation from before. The data points were 0, 2, 3, 1, and 1, 0. By looking at the system that would have to work in order for this line to fit on all these, fit all 3 of these data points, we set up a system of equations, we row reduced, and we found an inconsistency. The fundamental issue here is that we were studying a system ax equals b, where A here is our coefficient matrix whose columns are 1, 1, 1 and 0, 3, 1, and B is the vector 2, 1, 0, but B is not in the column space of this matrix A. So what do we do in this situation? We have an inconsistent system, so let's replace it with the least squares version of the system. The least squares version is the gramian of A as the coefficient matrix. And that, in this case, that's the matrix with columns 3, 4, and 4, 10. And then instead of B, 2, 1, 0, we look at A transpose times B, which happens to be the vector 3, 3. When I row reduce the least squares system, I do get a consistent system. And this is telling me that A naught hat should be 9 over 7, and A1 hat should be negative 3 over 14. What this is telling me is that even though I can't fit a line to this data, I can look at the line of best fit to this data, and that line is given by 9/7 minus 3 over 14 times t. And I went ahead and plotted that line, and we can sort of see here, like, yeah, this actually makes some sense. If I had to fit a line to this data, I would probably want that line to look something like this. I certainly wouldn't want the line to be sort of above all 3 data points, and I wouldn't want it to be below all 3 data points. So I would somehow want the line to cut through. And it turns out that the best way to do this, according to least squares, is for that line to cut through with slope negative 3 over 14 and y-intercept 9 over 7. We can also look at the error in this situation. And the error here is actually, we can actually visualize it. There are 3 terms in the error, which we are squaring. We're looking at 2 minus the line of best fit evaluated at 0. And that's the, what is that coming from? 2 is the first y-coordinate. And then we're looking at the line of best fit evaluated at 0 because that's the first x-coordinate. So what we're doing here is we're measuring that vertical distance and then squaring that number. Then we look at our next vertical distance, 0, which is our maybe second y-coordinate here, minus f of 1, where 1 is our second x-coordinate. We look at that distance and square it, and that is incorporated into the error. And then for the last term, we're looking at 1, which is the third y-coordinate, minus the line of best fit evaluated at 3, which is the third x-coordinate. We look at that vertical distance and square it, and that's incorporated into our error. So the error in this example can be visualized. When we solve a problem like this, so when we fit a line to data points in this way using the method of least squares, we call f hat, which is produced from this process, the least squares line of best fit. Now, I want to point out that this can be done in complete generality. Let's say that we were looking at the problem of fitting a line f of t equals a0 plus a1 times t to m data points, t1, b1, t2, b2, up to tm, bm. Well, think about what would have to happen if the line fit the data perfectly. So if every single data point was on one line. Well, that would give us a system, and the first equation would tell us f of the first x-coordinate t1 equals the first y-coordinate b1. And that's one row in an augmented matrix here. Then we get another equation, f of t2 equals b2. And we keep going with our equations here until we get to the last equation, which would be f of tm equals bm. And so now we know that if the data fit perfectly, this system, this augmented matrix, would be the data of a consistent system. Now, we have a coefficient matrix here. The first column is all ones, and the second column consists of all of the x-coordinates of our data points. And then we have our augmented vector here, which I'm calling b, and b consists of the data of all of the y-coordinates here. So now the idea is that generally these data points will not lie on one line, meaning that system will be inconsistent. So what we do is we look at the least squares version of the problem. We look at the Gramian of A here, which is A transpose multiplied by A. And what's cool about this situation is that even though we have m data points, so we might have hundreds or thousands of data points, and that would be the number of rows of A, when I look at the Gramian, I'm only looking at a 2 by 2 matrix. And I can systematically look at each coordinate. The 1, 1 entry of the Gramian would be the inner product of this row of ones with this column of ones. So really what we're doing is we're just adding 1 plus 1 plus 1 plus 1 all the way up to m times. So the very first 1, 1 entry in the Gramian here is the number m. What's the 1, 2 entry? Well, this is the inner product of this vector of ones with the vector consisting of all of the x-coordinates of my data points. When I take that inner product, all I'm doing is I'm adding all of the x-coordinates together. And actually, if I look at the 2, 1 position, I get the same inner product. I get the vector of all of the x-coordinates with a vector of all ones. That is also the sum of all of the x-coordinates of my data points. And finally, for the 2, 2 position in my Gramian, I'm taking the inner product of the vector of all of my x-coordinates with itself, which is really just the sum of the squares of all of the x-coordinates. So if you give me all the data points, this calculation automatically tells me what the coefficient matrix should be in the least squares problem. The other ingredient we need in least squares is A transpose multiplied by B here. Well, so when I take A transpose and multiply by B, I'll produce a vector with 2 coordinates. The first coordinate is obtained by taking an inner product of a vector of ones with the vector of all y-coordinates of my data. And when I take that inner product, I just get the sum of all of the y-coordinates of the data. And then the second coordinate here will be the inner product of all the vector organizing all of the x-coordinates of my data with all of the y-coordinates of my data. And so that's the sum of all of the products of each of the coordinates in each of the data points. So this is all the information I need to set up my least squares problem. So the least squares line of best fit would be f hat equals a0 hat plus a1 hat times t, where the coefficients a0 hat and a1 hat are obtained by solving the least squares problem. So we just found the Gramian, which has entries m and then sum of the t's in the 1, 2, and 2, 2, 1 positions, and then the sum of the t's squared in the 2, 2 position. And now we know we're augmenting with A transpose times B, which in the first coordinate is the sum of the y-coordinates, and then in the second coordinate is the sum of the products of all the data points. So if you give me the data, I can figure out all of these entries in the least squares problem, and then I can solve this system for my coefficients in my line of best fit. And then I get, and then I've effectively fit a line to data here in a meaningful way.